Again, when we talk about the least count, it is defined as the least count of an instrument is the smallest measurement that can be taken accurately with it. For example, in this meter ruler, if you take any adjacent two lines here, you can see it is denoting that's the minimum measurement, which is going to be 1 millimeter. And for example, you can try this by yourself, right? You can see this speedometer scale here. What would be the minimum measurement or the least count of this speedometer? And again, you just have to take out any adjacent two lines. And here you can see this is the 60 meters per hour, and this is the 70 meters per hour, and it is divided into 1, 2, 3, 4, 5 several parts. So which means that this is the next one is going to be 62, right? 64, 66, 68, and 70. So what is the least count then? Whatever the value in between this small gap, it is going to be 2 millimeters per second, right? 2 meters per second. That is the minimum or the least count. Right. Now we have to discuss about the errors involved with the measuring instruments, right? As I said earlier, the least error, the error in an instrument is the least count of that measuring instrument. The error is actually the least count of the same instrument. So that is what can be wrong, right? That is the value what can be spelled incorrectly, right? Or measured incorrectly. So what is an error? For example, if you are not using the equipment correctly, that is there's an error, right? So someone can think as, okay, these errors can be due to the, some of these errors can be due to the human errors, right? It is due to the incorrect reading or misreading of the instrument value, which can be categorized as a human error. And there are other different types of errors as well. So when it comes to the categorization, measurement errors can be divided into two categories: the random errors and the parallax error, right? The measurement error is defined as every time when taking a measurement, there may be uncertainty or an error may occur, right? Whenever we are taking a measurement. This may due to the person or least count of the instrument. Either it may be a human error or it may be due to the least count of the instrument. And all the errors can be categorized into these two, the random and the parallax error. We'll talk about these two separately. So when it comes to the random errors, an error in measurement caused by factors which vary from one measurement to another, right? For example, let's say if I am measuring the distance of this box, right? If I want to measure the length of the box, distance from here to here, right? From one measurement, from if I use the first ruler, it will take, let's say the value is going to be 1.5 centimeters, right? Or it may be 15 millimeters. And if I use another measurement or the same measurement, someone can get the value as 13 or 14 millimeters, right? Now you can see, if we are using the same measurement or different measurement devices, we will take different values, right? So each measurement is varying from one another. So that is called as the random error. And these random errors causes one measurement to differ slightly from the next. It comes from unpredictable changes during an experiment. And the scientists find out that the main reason for random error is limitations of the instruments, environmental factors, and slight variation in procedure, right? Environmental factors, when it comes to the instrument, in their handbooks or the manufacturer data list, measuring instrument has certain limitations. For example, we can use a meter ruler made out of stainless steel under a certain limited temperature, right? We cannot use it in higher temperatures, none other than denoted in this specification notes of that instrument, right? So what will be what happen when we use in such extreme cases? If we are using the measurement device over the limitations of the instrument, that causes the random errors, right? And slight variation in procedures. Example, look at these examples, right? Okay. When weighing yourself on a scale, you position yourself slightly different each time. Okay. That is slight variation in procedure. Second one, when taking a volume reading in a flask, you may read the value from a different angle each time, right? Different angle each time. It is something like this, right? Let's say this is the water level, and some person can look at this either according to the correct angle or from the top or from the bottom. So whichever the position you are using, you get three different values. However, the correct one should be this angle, right? This 180-degree angle is the correct angle. Next one, measuring your height is affected by minor posture changes. That is also another random error, right? As you can see, they are due to the limitation of the instrument, environmental factors, and slight variation in procedures. Moving on. Now here are the equation we can use and suggested for our A-level SFT module. The random error equations, there are two of them actually, right? I want you to remember these two actually. The first one is relative error, also known as the fractional error, right? Fractional error, it is the, if you want to find out fractional error of any measurement instrument, you have to divide it by least count of the measurement. So let's say we are using the meter ruler. What is the least count of the meter ruler? It is 1 millimeter, right? Divided by whatever the measurement or reading you take with the, let's say with the meter ruler. Let's say I'll measure up around 12 millimeters, right? So what is the fractional error then? So 1 divided by 12 millimeters, right? So sometimes it may be, let's say if you are taking the measurement as like this in different unit, let's say your measurement is 15.5 centimeters. So before you are slowing this down, you have to convert the centimeters to millimeters. Okay, so it is going to be 155 millimeters, right? 1 divided by 155. And if I ask the next question, what is the unit of this fractional or relative error? So millimeter to millimeter is going to cut out, or it is going to remove so far. If I convert the centimeters also into millimeters, we can cut out millimeters to millimeters. So remember, for fractional or relative errors, there is no unit. Okay, it is the dimensionless, or it is like a fraction. Yes, for fractions we don't have any units. And whenever you are solving this one kind of a fraction error, make sure to keep both values in the same unit, right? Otherwise there will be not a correct answer. And once you find out the relative or fractional error, you can multiply it by 100%, and there you can have the percentage error, right? With your measurement instrument, according to this 15.5 centimeter measurement, it can, you can say it can contain a percentage error of this much. So what is going to be the value? If I take a quick calculation, right? 1 divided by 155, it is going to be 0.006 multiplied by 100. So fraction error is going to be 0.6%, right? 0.6%. Can write it down like this here. 0.6% is going to be there. So you might have these kind of questions in the A-level paper actually, coming from these two. Okay, for each and every measurement instrument, it may be a vernier caliper, it may be a micrometer screw gauge or a traveling microscope. You might have to find out relative errors and percentage error. You only need two variables. What is the least count and what is whatever the measurement or reading. Okay. And second type after the uh, random errors, it is the parallax error. Actually, it is kind of a human error. You can see in this figure, the person is measuring the length of this wooden block, right? So depending on what is the angle he is looking at the final measurement, he might have different values, right? Parallax error, if you want to define it, it is the apparent shift in an object's position as it viewed from different angles. Parallax error actually can be seen or can be again learned in the engineering technology subject as well. Okay, when you are using a surveying equipment like the level machine, the parallax error with the surveying instrument as well, they have to deal with the parallax error, right? If you're looking from the top, you might have a overshot and you might have the correct level as well as the under volume depending on the eyesight, right? So you should always get the reading with the correct level. Uh, Also known as the visual error, you can see, even though I am reading a measuring instrument like a meter ruler, from this A, B, C positions, we should always take the correct level. Right here, you can see if I'm in the left side figure, there's a micrometer screw gauge, right? when you are also using this instrument, you should position it to the correct view, right? With the meter ruler as well, you can see if I use the correct level, it is going to be 4.8 centimeters. In the other parallax errors, it is going to be either 4.9 or 4.7 centimeters, right? So it plays a major role, right? And now we can talk about whatever the error you can find out, right? As I said earlier, there are also measurement instrument have has mined out in the zeroth error, right? Whatever the instrument you have to be dealing with, sometimes they might have certain wear off, right? There may be certain errors included in the instrument. So that kind of case, we have to talk about this zero error, right? It is the zero error, right? If there's no error, actually zero error is the it's best to, if any instrument have a zero error, it is also okay. However, zero error can be divided into two parts: the positive error and negative error. Now, if whenever you have an instrument with this kind of error, you don't have to throw it away, right? You don't have to buy it a new one. Instead, you can find out, okay, what is the error included in the measurement. You first of all find out what is the error. Then accordingly, you can take measurement, and if it is a positive error, you are going to reduce it or subtract it. If there's a negative error before you are taking any measurement, okay, if it is a negative error, you can take the reading as the second step, and then you are going to add that negative error into the final reading. So then you can have the correct value, right? Okay. The systematic errors, also known as the zero errors, are caused by fault equipment that doesn't reset to zero properly, right? In the laboratories, you might find this measuring instrument. You don't have to throw it away, right? You don't have to throw it away. Instead, you can reset it, or you can just use it with the error. However, we have to initially find out the error first of all. And especially when the jaws of the calipers, here we are talking about the vernier caliper, I will show you a figure, right? When jaws of the caliper and screw gauges are aligned, if the zero mark does not align with each scale, will be the result of an zero error. For example, right? If this is the vernier caliper, there is a main scale as well as a vernier scale, okay? Right? So before we are taking any measurement, right? Here is the main scale. We'll talk about these things thoroughly. Here is the vernier scale. And both scales have zero mark on top here, as well as in the vernier scale. Right? Before using this machine, this zero to zero, the scale zero should be aligned perfectly, right? It should be aligned perfectly. So here still I am talking about the vernier caliper. I will show you the figures for you to understand easily. Right. So sometimes this due to the damaged or the wear off of this jaws of the vernier caliper, right, or the micrometer screw gauge, what happened is that sometimes this zero line might change to this position. When the jaws are aligned, now the zero is moved to the right hand side. Zero is moved to the right hand side. Okay. So this is called as a positive zero error. This is called as a positive zero error. Why we call this one as a positive zero error? Because whatever the measurement we are taking, there's a small positive value already included as a positive value. Let's say, first of all, we'll take the instrument. We have to find out whether it is a positive error or negative error. And if the vernier calipers, sorry, the vernier scale zero is aligned to the left hand side, this is called as a negative zero error. Okay. So whenever we are taking a measurement, we will find out what is the error, right? Let's say, okay, the vernier caliper. Let's say there's a positive error. We can find out the positive error. Okay. Positive error, let's say it is going to be 0.1 millimeters. Let's say 0.2 millimeters. And here we can have the reading or the measurement, right? We are going to measure anything we want as usual. Measurement. Our measurement is going to be let's say 12.5 millimeters. Now, obviously, the reading is incorrect, right? Because there's already a 0.2 millimeters already added to this value. So what is going to be the corrected reading? The corrected reading can be 12.5 has to be subtracted from the positive error. It is going to be 12.3 millimeters now. So this is how we are going to use the zero error, right? Whether it is a positive or negative zero error, right? You should always check for errors, systematic errors or zero errors before using any kind of instrument. And as I explained earlier, positive zero error refers to the case when the jaws of the vernier caliper are just closed and the reading is a positive reading away from the actual reading. Right. You can see in the left-hand side figure, when the vernier caliper's jaws are aligned perfectly, right, in the main scale as the vernier scale, you can see zero and the vernier scale zero is aligned perfectly. So there's no error in this side because this is a usual one. We only concerned about align these two zeros, aligning these two zeros on top of each other. Okay. And positive error means, as I said earlier, the vernier scale zero shifted to the right hand side, right? There's a small gap. So this small gap is going to be the positive error. So you can usually use this measurement instrument to measure anything. But however, this positive error has to be always subtracted from that final value, right? Okay. Right. So we will find out this positive error, right? I hope you can see the screen here. So this is a vernier caliper. These are the claws, right? These are the jaws actually to measure the external lengths, right? External diameters. These are actually the claws. This vernier scale, this part can be, this is a movable part, okay? This is a movable part. And you can see here, these two zeros are not aligned. So obviously it is a positive error, right? And if I ask, can you find out the error actually as it is? Now, you might learn this one from your school, right? It is also okay. The vernier scale or the vernier instrument, this is how it is. The concept I will explain now. We can make a vernier caliper or the vernier part like this, right? You should always have, first of all, a main scale, right? Main scale, let's say, we are going to take 0 to 1 centimeter, which means 0 to 1 centimeter means it is 10 millimeters, right? And we are going to divide this length into 10 several parts, 10 separate parts, right? You can obviously see that one in this figure, right? Then you can take the vernier scale. You can take the vernier scale. In the vernier scale, what happened is that you can take 9 parts, right? You can take 9 parts. You can take from the main scale, you can take it to 0 to 9 millimeters, and from 0 to 9 millimeter, you are going to again divide that vernier part into 10 separate values, right? So 9 millimeters again divided into, so here to here it is 9 millimeters, this distance, right? This distance is going to be the 9 millimeters. 9 millimeters again divided into 10 parts. So with that concept, we can actually measure up to 0.1 millimeter accuracy, which means the least count, if you are using this kind of a vernier scale, you can measure up to, I mean, for a usual meter ruler, what is the least count? Meter ruler least count is 1 millimeter. However, if you are using the vernier concept for especially the vernier caliper, it is going to be 0.1 millimeters. So accuracy is somewhat increased, right? You can increase it more further if you are using the micrometer screw gauge. So there's a different concept for the micrometer screw gauge, okay? Right. So we'll again talk about these things thoroughly. I just want to show you several facts. Right. Now, since we have to find out the positive error, actually you should know how to read the vernier caliper, vernier reading, right? I hope you can see this figure clearly. So this is how you are going to take the reading of a vernier caliper. When you come to vernier caliper, I will again explain this one. But let's see what is this positive error and how to read this value correctly. So as you can see here, we have the main scale and the vernier scale, right? Vernier scale at the bottom, right? Now this is how we are going to read this one down, okay? If there is no error in the measurement, which means here that if there's a 0 error, usually this 0 to 0 is aligned. And all the other parts are not be aligned. Only this 10th part is going to align with this 9th millimeter point, okay? However, as you can see, there is a positive error. I would say this is a positive error because the main scale 0 is situated left side to this vernier scale. Usually the vernier scale should be in align with the one, but if it is moved to the right, it is called as a positive error. Now this is how we are going to read down the value, right? First of all, remember whatever the value you are going to read is actually the, I will use the red color. Whatever the value as the error you are going to read out is the distance between this small gap, which means the 0 to 0 distance. This small distance is the positive error, okay? This is the small reading we are going to take. So as obviously you can see, if you are starting from the 0, the main reading from the main scale, the reading is going to be 0 millimeters, right? 0 millimeters. Plus, from the vernier scale, this is how you can read out the vernier scale reading. You have to find out which part is going to coincide with the main scale part, which means you can see if you look at the third part of the 10 division from the vernier scale, it is aligned with the main scale part as well, right? This from the main scale part and the vernier scale part, this line is aligned. However, you have to read this one not from the main scale but from the vernier scale side. So it is going to be 0, 1, 2, 3. Third one is aligned, okay? Then I would say plus 3 parts multiplied by the least count of the vernier caliper. The least count of the vernier caliper, which is going to be in that case, in this case actually 0.1 millimeter. I'll show you how to find out the least count of a vernier caliper. We have to do some questions regarding that one as well. But in this case, you can see the final answer is going to be how much? 0.3 millimeters, right? So this is the positive error. This is going to be a positive error. But the correction is what? The correction is negative correction, which means negative correction, which means once you get the reading, you have to subtract the 0.3 from the whatever the reading you take. Right. So it is all again explained in here, right? Calculation of the positive error coincide in vernier scale division. Vernier scale division, okay, it is not the main scale division, but most students are confusing when it comes to reading the coinciding part. It should be calculated or read out from the vernier scale. So it is going to be 3 multiplied by the least count. It's going to be 0.3 millimeters, so 0.03 centimeters. Okay. So I just take in the previous one, I just take the millimeter reading, right? And you can say thus it is a positive error. It is indicated with a plus sign, right? So how to correct the positive error? True value or true reading is going to be the observed reading minus positive error, minus positive error. Right. So I think this is a weighing equipment actually. This is the weighing equipment. But as you can see, there is a small error. It is actually positive error. I think it is not clear for the screen, but I can indicate in here. So this is the 0th point. This is 5, let's say 5 grams. This is 10 grams and 15 grams. So at the rest position, it is the the arrowhead is indicated to the not the 0 but to the 5 grams. So what is the error now in this case? You see, it is a positive error. First of all, it is a positive error. I can say this is a negative error if the arrowhead is located somewhere in the other opposite side. But in this case, it is a positive error. And what is the value? Positive 5 grams, right? Positive 5 grams. So then we can talk about the exact opposite, the negative 0 error, right? The reason for the negative 0 errors is when the jaws of the vernier calipers are just closed and the reading is a negative reading away from the actual reading 0 millimeter. If the reading is 0.1 millimeter, the 0 error is referred to as minus 0.1 millimeter. And you can identify is that this is due to the wear off of the jaws actually, right? Due to the long use, right? Due to the long use, what happened? The mechanical parts and the steel parts is going to wear off, right? That is the main cause for the negative error. But what is the main cause for the positive error then? Let's say there's a little bit of dust, or let's say the rust particles, the corroded steel parts are in between the jaws. So as the error, you can, as the error, positive error, you get the value, you can get the actually the thickness of that corroded part. That is the error. So the exact opposite, due to the wear off of the jaws, the zero of the vernier scale is on the left of the main scale, right? So to get the correct value, you can use still the measurement device, but you have to add that negative zero error. Right? In this weight measuring instrument as well, this is the 0th point, and you can obviously see at the rest position, it is located to the opposite side. So this is going to be a negative 5 grams, right? Okay, here you can see the negative error, right? You can pause the video for a second and find out what is the value of the negative error. You can put a comment on that. And here is, as you can see, obviously the vernier scale 0 is shifted to the right side than the main scale. So that is how I can find out this is a negative error, right? Then what is the value? How to find this error? As I said earlier, this is the error. The difference between these two zeros actually. This is the negative error, right? So you can first of all find out the coinciding line between the vernier caliper and the main scale. So it is going to be the 8th part, right? 8 division. From here it is 8 millimeters, right? So can you then, I think you can identify what is the difference. So if I take from the main scale, remember, if I consider the main scale, what is the distance from this 0 to this 8 millimeter point? So there are 1, 2, 3, 4, 5, 6, 7, 8, right? Which means this distance I denoted by red arrowhead is 8 millimeters. And can you find out the distance from the vernier 0 to this 8 millimeter part? Sorry, not 8 millimeter, the 8 division. What may be the distance? So I didn't taught you this one, but actually, as I said earlier, the vernier is that the 9 millimeters are divided into 10 divisions, right? Which means this is the 9 millimeter point, and this 9 millimeter is again divided into 10 parts, right? So this 9 millimeter is divided into 10 parts. Then what is the, if I take a one vernier scale division, what may be the length? So from here to here, it is 9 millimeters, and 9 millimeter divided by 10 means it is going to be what? 9 divided by 10, which means this one single vernier division is equal to what? 0.9 millimeters, right? 0.9 millimeters. And what may be the distance now? 0.9 millimeters multiplied by how many divisions? 8 divisions, right? Which means it is going to be 7.2 millimeters, right? Can you scope what I have said right now? So as I said earlier, 10 main scale 9 millimeters is divided into 10 divisions in a vernier scale, which means that 9 millimeters divided into 10 parts, which means one division is going to be 0.9 millimeters, and 0.9 millimeters multiplied by how many parts? How many divisions I have to consider? There are 8 divisions. This is the coinciding line, right? So from the top, from the main scale, it is just 8 millimeters, but from the bottom, it is 7.2 millimeters. So this is where you can find out the negative error. This is the gap, or this difference between this 8 millimeter and 7.2. So it is going to be how much? the negative error is going to be 8 minus 7.2. It is going to be 0.8 millimeters. And this is a negative error, so I can put negative sign in front of that. Or in most cases, engineers tend to apply these brackets for any minus value, right? Engineers are tend to use the minus for in minus and the bracket for any minus changes, right? And this is how you can take the negative error. You can measure anything, but however, you have to add the negative error for to get the true reading or true value. So this is also one example, but as you can see in this case, the vernier scale and main scales they were transferred into the opposite side, right? So whatever in that case, we can also find out the negative error. It doesn't matter.